Select the major product of the following reaction. And so in looking at something like this, we've got quite a few things. So we've got this aryl halide. So aryl just means that the halogen is directly attached to a benzene ring. So we have an aryl halide. And then we see what we are reacting it with is this organoboron reagent. So we see that boron. So we see an organoboron reagent. And then we see a palladium catalyst. So in this case, the L2, L just stands for ligand. So these tend to be big hydrocarbon groups typically. And hydroxide is a base. And so what we need to do is we need to be familiar enough with a couple of palladium catalyzed reactions to be able to identify which one this is. So this is in the section of our textbook on palladium catalyzed coupling reactions. And so there are two that we're going to focus on. And so this here is an example of the Suzuki reaction. So let's just look at a quick overview of what the Suzuki reaction is. And so this is a reaction, we'll say Rx, but this R has to be either aryl, like we see here, or a vinyl group, so like an alkene. So it's actually a halogen attached to an sp2 hybridized carbon. So we have an aryl or vinyl halide. And then what you're reacting it with, we'll say a different R group. And this is going to be an organoboron reagent. So an organoboron. And you need to have the palladium catalyst in there as well as the base. And so what happens in this reaction is you basically just bring these two R groups together. And that's why this is called a palladium catalyzed. We've got a palladium catalyst, but coupling reaction because we're coupling these two pieces together to form a new bond. Okay? And so what gives this away to me as a Suzuki reaction is that the Suzuki reaction is specifically the reaction of an aryl or vinyl halide with an organoboron reagent. So it tends to be the presence of this organoboron reagent that makes me think about doing a Suzuki reaction. So we want to do, we've got this kind of general format. We want to apply it to the system that we see here. And so we want to identify the carbons that are reacting in this. So it's going to be the carbon, the sp2 hybridized carbon where your halide is attached. And it's going to be joining to the carbon that is attached to your boron. And so essentially you're snapping together these two pieces. And you can see that we have an alkene, that is where this boron is. And so we're replacing this boron with this aromatic ring exactly where it was. So we want to pay attention to the stereochemistry of the alkene. So we had an alkene that was trans. And when we snap these two pieces together, we maintain that stereochemistry. So that means that when we form our product, we're going to have the benzene ring. So this is one of those two carbon atoms right here. I'm just going to highlight where the iodine was. And this is forming a new bond to this carbon atom here. That is the first carbon atom of this alkene. And so there's the alkene. Right? And so here's where you want to make sure that it's trans. So the bond to the boron was going down. We've got the bond to the aromatic group going down. And then on the other side of the alkene, the rest of this alkyl chain is pointing up. That's that trans relationship. So I want to make sure that's pointing up. And we just have 1, 2 carbon atoms. So off of that other side of the alkene, we've got 1, 2 more carbon atoms. And we could number these too if we wanted to keep track, just to say this is where they attach to the ring. Right, so this 4 carbon atom fragment is being coupled to this aryl halide, and we're maintaining the stereochemistry that was present in that alkene. So you can see that here. So you can see the 4 carbon atom chain that bound to the aromatic ring, and we can see that we still have the trans stereochemistry. And we should recognize that that is C, where we have those 4 carbon atoms, and we have the trans alkene. And so if we wanted to make the cis alkene, such as in B, we would just have to start with the cis organoborane. So you could swap this boronate ester with that hydrogen so that you have the cis stereochemistry, and that would allow you to make something like B.